Hey everybody, it's Mr. Szabo again. This is video 2 of our function operations series, and this one is going to focus on multiplying and dividing functions. I'm starting right away with information about the domains. So, couple things. Just like with the sum and the difference, the domains of the product and quotient, multiply or divide, will consist of x values that are in the domains of both the original functions. So we need to combine those domains, but there's one additional restriction. Specifically, when we are dividing, when I have f divided by g of x, or f of x divided by g of x, the quotient, the denominator function, cannot equal 0. And we'll see examples of that as we get into the notes here. But we can't divide by 0. That is not a function that's defined if we have 0 in the denominator. So we have to restrict our input values so that we don't get that to happen. Now, one additional thing before we get started with examples. I want us to pay close attention to the symbol that we're using for multiplication. This is going to come into play later on in our third video as well, but that's a completely filled in circle, and that's going to make a big difference. This says take function f and multiply it by function g with the input value of x, or f of x times g of x, whereas f over g of x is the same as f of x over g of x. And once again, no matter which form we look at this, your g of x function, or specifically your denominator function, cannot equal 0. So before we even start to find the product of our functions, and this time we're not naming them f or g, we're naming the functions h and k, I want to find the domain of each function. For function h, the domain is all real numbers. There's no restrictions on what x could be, but I cannot have x be 0 for function k, because I can't have 0 in the denominator, and it's just a monomial, linear monomial of x in the denominator right now in k. So k, function k, my x can't be 0. Now, this dot, h of k of x, or h times k of x, same thing as saying take function h of x and multiply it by function k of x. So this is going to be a multiplication function. I'm going to take the two functions as quantities. And I'm going to take function h of x, which is 3 minus x, and multiply it by function k of x, which is 1 over x. This is the distributive property. 1 over x times 3 gives me 3 over x, minus 1 over x times x gives me x over x, which that does definitely simplify to 1. So my function h times k of x is going to be equal to 3 over x minus 1. X divided by x is equal to 1. There's my new product. What is the domain? Well, it takes the domain of both of my original functions, all real numbers, but also x cannot equal 0. So I know that this domain will also be all real numbers such that x is not equal to 0. I'll write that in set builder notation. In the second example, it's now asking me to divide my functions. It's asking me to take function h of x and divide by function k of x. So my domain now, I know that k of x cannot equal 0. Well, k of x won't equal 0 anyway, because it's 1 over x. So I'm not going to be worried about that second note for my domain in this particular problem. But I do have to set up my quotient. Function is h of x. I get 3 minus x in my numerator, and divide by k of x, which is 1 over x, in my denominator. We don't want to leave it like that. We don't want to leave it as a complex fraction. So, dividing is the same as multiplying by the reciprocal. So if I have 3 minus x in my numerator, instead of dividing by 1 over x, I'm going to multiply by x over 1, the reciprocal, which means I have to distribute again. 3 times x I get 3x minus x times x, that's x squared, and it's all over 1. I can leave it like this. Fortunately, I don't want to leave that as my final answer because that's not in standard form. So, in standard form, h over k of x is going to be equal to negative x squared plus 3x. There's my standard form, the quotient of function h divided by function k of x. And the domain is going to be x such that x is not equal to 0. That's the domain of both of the original functions. The second aspect of the domain, the second restriction, the quotient cannot equal 0, is already taken into account. Now we have one more example that we want to talk about. If you want to press pause on this video and try both of these before I go over them, please do so now. I'll give you a couple of seconds to do that. So for part A, we're taking function f of x times function g of x. Again, make note of the mark here. And we're multiplying these. Well, this is a binomial times a binomial. That's also known as the distributive property twice. I don't like to use that four-letter F word. It only works with binomials. So I'm not going to FOIL this. Oops, I used it. Anyway, x times x is x squared plus 3x. Negative 1 times x is minus 1x. And negative 1 times 3 is minus 3. Combine my like terms. I get that my function f of x times my function g of x is equal to x squared plus 2x minus 3. There's the product of these two functions. And as far as domain goes, I have no restrictions for f of x, no restrictions for g of x. There's no quotient here, so I don't have to worry about the extra restriction. Therefore, my domain will have the same domain as these, or all x values, such that it's all real numbers. Be careful on part B. This one is set up so that I have g of x divided by f of x. G divided by f of x. So it's not always whatever comes first as far as what's listed here. You got to pay close attention to the notation. G divided by f of x is the same as g of x divided by f of x, or x plus 3 divided by x minus 1. Another reason I like to put these in parentheses, the quantities, is this indicates that I can't simplify x over x. That's a binomial over a binomial. A lot more to come on that as we get further on in the school year. But understand that nothing simplifies in this case, and we are just left with x plus 3 over x minus 1. That is our quotient, g of x divided by f of x. So now we got to talk about the domain. Well, the domain of f of x is all real numbers. The domain of g of x is all real numbers. So the domain of the quotient takes on all real numbers. However, this is where the extra restriction comes into play. Since f of x is my denominator, f of x cannot equal 0. That is a restriction that I have to add. And since f of x is equal to x minus 1, f of x, cannot equal 0. Therefore, x can't equal, when I add 1 to both sides, 1. That's a new restriction for my domain. So all real numbers, but not positive 1. That would make my denominator 0. So I would state that my domain is all x values such that x is not equal to positive 1. The one trick, or the one catch you have to be careful of is, it didn't happen here, but if I had say a trinomial in my denominator and the trinomial can't equal 0, maybe I have to factor that and I have more than one restriction. But keep that in mind as you're working on our homework assignments, and as we get further along in the semester and we start talking about simplifying these rational expressions and talking even more detail about the domain restrictions.